Okay. Hello everyone. Just give me like a few seconds while I get myself seated. Okay, tag. Okay, perfect. How's everybody doing? Hey, how are you, man? Okay, just need to post that here. Okay. Over here. Okay, perfect, good. And okay, so this is there. It's a lot of stuff to get just like this properly shared. It's TRM review all the way. Okay. So how's everybody doing? Hey Pratik. Oh, you're traveling. No worries. This is recorded, so it's fine for you. Cool. Have a nice trip, man. Where are you going? Hi, Sajay. Okay, we're doing good here, and over there, this is where I'm gonna see the Twitter chat. Technically, yes. Hey, good to see. How are you doing? Hey, Sharp Eye. You can't hear well. Are you? Is it better? No. How is it my mic not working? You sure? Hey, how's the sound, folks? Does it sound good? Oh, okay, cool. Just hometown travel, cool, man. Yeah, just take a full week to meditate. Streaming VLMs. Oh, that's a good idea. I think I never actually dived deep into streaming VLMs. We'll take a look at it. Okay, now it's good. Perfect. Cool. Yes. No, not too late. We're just getting started, folks. So today's paper is the TRM paper. 12 pages, honestly. Like it's not that bad. You should all check it out. Absolutely awesome. It's one of the best paper I've read this year. Like, no joke. I know it's like a one-person paper. But it's just so good. Like there's different like flavor of research that you see, but like once in a while there is that kind of paper where the idea is simpler than what was there before and so well distilled into its essence, right? And like all of your questions that you might have are already being answered in like the most sharpest way possible. There is some criticism here because she didn't do all the references that are possible for like latent reasoning. But I think it's kind of fair because HRM was already like referring to this paper, and then she specifically referred to HRM like and all this stuff. There may be this kind of broader look at it, but it's specifically a paper about HRM and then how to make it simpler. So I don't know. I give her a pass for this because it's just such a good paper. So you should definitely check it out. Absolutely love it. And there's all sort of tidbit of information that like are all over the place. Like for example, like the ideas that she tried and she didn't work out and all this stuff, which is rare to see somebody actively like telling you what didn't work out. She did. Which and in a way that adds to the overall story also. Like you can just say like, hey, we tried like these 7 things and they didn't work out. Like no, it's like we tried these and it taught us this thing, right? But before we start, I want to just to remind everybody, this is just a front, right? The whole purpose of this live stream is just like, I don't know, man, like to have a chat and have like, if you have any question, I'm gonna stop the stuff and then just answer them as we go up. Yes, the paper is cool. It's nice research, but it's more of a place for you to exchange and then just ask any stupid question you have. By the way, I went to like a conference 2 weeks ago. I asked the most dumbass question, right, to the top researcher in front of everybody, and I took the mic. Like for every conferences I went, I did that. Every talk that was there, I just took the mic and asked my dumb question, and I looked like the researcher in the eyes, and I didn't budge until like they answered my question. So if I can do it in front of everybody, you can also do it here, like on the chat. So do it. It was a nice conference. Cool. Before we move on, we have a few questions here. Make a series on VLMs. Yeah, I think I should. Like VLMs are super interesting. The last video that we did, there's Alexine that showed like a kind of VLM and how to do like reasoning on it. Super good. Hey Adam. Hi Santi. How can you all do all this research thing with your business in parallel? Do you apply many of the things periodically on your company? Like I've always done this. Like this is a good question actually. Like we're not even started yet. I'm reading the question on the chat from YouTube, by the way, and from Twitter. So I have the two of them together. The question is the following. Like, am I unemployed? How the fuck do I do that? How do I keep up with all of this? So this is the question. I'm just gonna highlight it here. Over there, right? So how can you handle all this research thing with your business in parallel? Do you apply many of the things periodically in your company? That's it. Like, it's always good to like look at research, right? Because, but like in a very specific way. So there's two ways I'm looking at research. There's the very practical and pragmatic way, which is I need to get this thing done and I need to have the details information about how to do it. And then there's another way, which is I want to have more ideas, right? And like I have to understand where stuffs are going, right? And both of them are super useful because if you're doing none of this like more idea thing, when you get to encounter a problem that you have no ideas about, right? You're just gonna be stuck and nothing will move. Being able to come in, swoop in with your team and just being able to say, I've saw this pattern before. Have you tried this, that? You can cut off like months of work, right? So there's this thing that is happening. The second thing is that if you have a practical thing to like try to clear up, I never go for the fancy stuff. So like there's no way you're gonna implement any of this stuff in like actual like business sense. There's no way. Like a puzzle solver, right? Remember guys, what we're doing here is like Sudoku solving that thing, right? So there's no use case whatsoever. Like you could technically have a deterministic algorithm that will do better than this. So it's not about that. It's not about RKGI. It's not about the solvers. It's not about the maze. It's about the implication of it. So test time scaling is what I'm getting out of this, right? So yeah, that's my thought. And like, as you do more stuff in like business sense, like I have the chance of being a business owner, right? Like I own my business, and like I'm most likely gonna do another business in the future also. Like it's not I don't have like a very fixed type of thing that I need to do. I mostly like unlock my team and then like help them out figure out what to work on. So that's kind of the stuff. Fantastic question to kick this off, my man. Okay, so we have a lot of ideas here for next video. Thank you very much. I will check out of this. Thank you, Pratik. Have you found any good LM-based tool that help you with discovering and reviewing papers, especially with how quickly they come out? Twitter is a fantastic tool for this, to be honest. Yeah, if you follow the right people, like they will just tell you, and then you look at the ideas, right? And since it's like very sharp type of information, you can quickly like figure out what you like. So you like the post with like good researcher put out, and you bookmark them, and like at least once a week I just print a paper and I literally read it like top to bottom with annotation. I'll try to do this every week. There's a lot of other paper that I'm just like quickly skimming, but that's kind of the idea. So no, Twitter for me is like, there's also Alpha Archive, I think it's called, but that I never like there's not a feed that is better than that in my view. Okay, this is good. Trying to wrap my head around how we have this immediate and easy implementation in your company, which is very supply chain oriented. No, there's no implementation of TRM or HRM or any of these reasoning model in supply chain. LLM's easy to implement because like there's like workflows, but even there, folks, like most of the time you don't need to reach for the fancy thing ever, right? Most of the stuff can be solved with like very simple things. And you should always reach out for the simple thing first and fast so that you can get the job done. Hey, Salvatore from Italy. Cool, man. How to find a research gap to work on the research topic? I'm going to show you because literally in the papers, they always tell you. So this is good. Good. Well, let's get it started. Before we start, this is a big boy live stream now, right? So we're actually gonna do thanks our sponsors for this today live stream, which is Scrimba, right? I really like the guys, honestly. Like I started the sponsorship with Scrimba because I literally a guy is called Daniel over there. I just reached out to him and I was like, "Yo, I love the platform. Can we do something together?" So really like them, and most of their stuff was front end in the start, right? It's like a learning platform, but now they're going into other directions. So there's like the whole AI engineering type of thing, the whole backend type of stuff that you can now learn in this. There's the full stack developer path, which is like 100 hours worth of content, right? And a portion of it that is super relevant for you guys is the AI engineering one. So like the question about how to apply this type of stuff in business, most of the stuff right now is not like the research type of thing, right? The research type of thing are super useful if you're more in a research kind of role, research scientist role at these big labs or like these companies, right? Like for example, Alexia is in the Samsung lab, right? Which is a big lab. So this is why she's doing like this type of research. But like what is usually useful in business right now is just how to cobble together a solution with AI. So this is a super good kind of course, right? And what I like with all this stuff is that like how it's written, how the whole thing is set up is that you have the whole videos and stuff, and then you can watch it, and then they're gonna help you set yourself up with whatever. But then at some point, right, you can just take control of this whole thing. Like you can take control of the ID, and you can run the code. And there's like all the stuff that you need to run this stuff, right? So you can actually test yourself, and you don't need to get set up in your computer if you need to. It's all on their server, and then it's all working like that. You can actually download the whole thing afterward as a zip. Well, wait a second. Here, right? If you want to kind of take it and crank it up a notch. But that's kind of that. Like everything is there for you to do your things. And like the AI engineering portion makes sense from a learning platform tailored toward like front end people, because most of the stuff you're gonna do is like duct tape like API calls together and then wrangle this stuff up, which like has this kind of front end type of flavor, like even like software engineering type of flavor. So check them out, and many thanks Scrimba for sponsoring this. Really appreciate it. Cool. So TRM, let's take a look at it here. Sorry man, like I have a lot of stuff for you, right? So we're gonna be able to check them all of them here. Do you have questions? Wait. Now GPT from Andrew recently. I think it's really interesting. You're going to make a video for it. Oh yeah, I could make a one. There's also the speed runs that like Andre is running from time to time, which is super interesting. Share this website link in the chat. Yeah, for sure. You can check it out here. There's also like a 20% off with my link in the description, but like you can just check that over here. Perfect. So let's get, what an honor to be in a canvas. Let's get started. So the TRM is this paper, link is in the description, And like how you should think about it is like, think about the HRM, and it's a distilled version of the HRM, right? So if you looked at this video that we've made with Julia, this one, oh, look at this glow, right? It was a peak summer. Now I look like I need a bit more sun. So check this one out, because in it I go through the full kind of breakdown of like the HRM architecture, and it was not easy because it actually looked like this. This is the HRM, right? It's this whole thing. So there's like, it's like Inception. You see in Inception there was like these 4 layers, right? And in the last one you don't know if it's real or not. It's the same idea. You have this big gigantic harness on top of like this stuff that is like kind of recursing in like 3 different level. It was very, like, honestly, it was one of the most spaghetti like shaped structure that I ever saw. So, and there was also like some biologically inspired thingy in there, but like I was not, it didn't sit well with me for 2 reasons. Because like at first I was confused because I thought it was like human related like synchronization, which it was not. It was mice. And even in the mice direction, there's something missing, because like it's not just like 2 frequency and then you're able to do stuff. There's this whole architecture and then this whole kind of other things that are happening in order for the mice to do an action, which is not just like 2 frequencies and stuff like that. Anyway, so what she did is she just like filtered everything that like didn't make any sense, right? So she filtered out, she simplified, and then she cut all the noise, which was beautiful, right? A bit, I think I've posted about this. It's a bit like, I don't know if you guys remember that, but like, it's a bit like the highway network with the residual neural network, right? The highway network appeared like before the ResNet, but the ResNet just took what the highway network did and simplified the hell out of it. So now it was like super simple, and like this took off. It's kind of the same thing that we're seeing live now. Like this thing is taking off because of the simplicity of it. So all of the complicated stuff are kind of removed. It's not a one-to-one, but like, I mean, you get what I'm saying. Perfect. So like the whole thing looked like this, right? It looked like there's 2 things, but it's just like, it's just this part, right? And here there's a 4, but actually it should be a 2, right? And that's that. Like the actual thing is very, very simple. There is some self-attention over here, but it can also just be a MLP. There's the MLP that is over there. So this is literally a multi-layer perceptron. And then the whole thing works because of how the data flows into this network. So you see we have the input question that goes in, we have the predicted answer, we have the latent reasoning, and this is acting as gate because sometimes we're not gonna give this, we're just gonna give like that and that, and sometimes we give the 3 of them, and then there's kind of 2 loops going on. There's the blue loops, right? And then there's the yellow loops, and like this whole thing is gonna recurse on the purple loop, right, which we're not seeing. So this is what we're saying, right? So there's gonna be the blue loop that will go like this for n time, and then there's gonna be the 1 loop with n+1 over here, which is gonna be the yellow stuff, which is updating the prediction, right? And in the blue, it also take the y. It doesn't just not take it. You need to also give it the y in order to be able to like figure out where you're at. And then the purple stuff is just like you repeat this stuff at most 16 times, but usually it's gonna be less than that, but at most that much time, right? And this will be your big T, right? And like this whole thing, we're not gonna be, when we're gonna train, we're not gonna like do back propagation on the whole thing every time. We're gonna do a bunch of things. So in HRM, we did only at the last step, but here it's a bit different, but it's much simpler. So that's the gist of it. There's no 2 architecture doing like, this is the strategic folks and this is like the operational folks. Like this is it. So this is like the operation, right? So like the low level operation, and this is the strategy, right? So in HRM term, she just combined the 2 into one network. And then she did something that like I think was a bit lacking in the HRM, which is like she did a whole bunch of ablation studies so that you can actually look at the driver properly. Yeah. So that's the gist of it. And doing this with now it's 7 million parameters versus 27, I think, for the HRM, make it much better. It generalize more, and it's just better in like on like the ArcAGI 1 and 2. It's better than all of these bigger network. Yeah. So that's the gist of it. And there's required none of the weird stuff. So there's no fixed point TRM. So this is out. No complex biological thing. There's a very specific reason why you need two things going in parallel. Well, not in parallel, but like you need the high level and then the low level. They tried the 3 and the 4th levels, and they tried just one, and it didn't work as well, right? So the 2 worked good, and they work good because like some of the stuff we're gonna see it afterward over there, here in the Sudoku, right? The thing that is closest to the actual response when it goes into the linear layer is actually the response in latent space, and the other thing is not. It's like the chain of thought scratchpad. So that's the reason why you have 2 things, right? But then you can just update these in the same parameter space, and you should be good to go. So yeah, that's the idea. And remember, like what we're doing is grid of stuff, right? So somebody said like this kind of feel like a diffusion process with how the final prediction is slowly refined. It's exactly like that, right? Well, and not exactly like that because it's not a diffusion thing, but you have the whole thing given, right? And at first it's just complete garbage, right? And then like it will iterate through it, right? And then like it will change the whole thing every time, right? And then until it's good enough, and then you will shoot that up. But that's literally like what the diffusion process is doing is like is gonna propose the whole thing. At first it's gonna be garbage, and then refine this. So this is what we're seeing, and it's like doing reasoning because like it's mimicking a bit like the chain of thought type of stuff with the scratch pad that you have on the side. And I was waiting for this to make this live stream, just in case like actually we fucked up something. But no, like the TRM folks, the art prize folks said that like this is super legit. It works on 1 and 2. It's like very close, right, for the validation. And they also said that it was well witched and everything. Honestly, it's good. It's a good thing, right? So check it out. Everything is validated here. It's great. Where is the HRM in there? I don't think they. No, I think they're not showing it. No, they're not showing it. So that's that. So this is the overview. Any question before we dive a bit into the HRM? We're not gonna go like deep in it, just so that you see which part are important. Okay. So, right, the HRM. I don't even want to dive too deep on it. There's 2 things in the HRM, right? There is there's kind of two main driver, right? First driver is the deep supervision type of stuff, which is this kind of like a latent reasoning type thing that is going, right? So it's like the bigger outer loop. Actually, there's 3 things that are important. There's the bigger outer loop. The second thing is the hierarchical structure of it, right? And the hierarchical structure with the NDEA people, so that's like I think it's Francois Cholet company that is doing consulting stuff. They validated that like wasn't super duper important, right? It was mostly like the deep supervision stuff. So there is some improvement, but not that much, right? You can actually remove that weird setup with transformer and you should be good, which is kind of where the idea of TRM spurred out, because if you don't need that, can we just make the deep supervision thing much better? Actually, the hierarchical structure is kind of important, but you don't have to have it in 2 things. You can have it in 1 thing, right? And you don't need to like have all these fancy weights like that are different. You can have 1 set of weight, and like that's that. The third thing that is important, that is also super important in TRM that you should not forget, is the amount of data augmentation that we're doing. So Like we're not in the regime of like this thing is pre-trained on like internet scale type of stuff. It doesn't know anything about language, like zero, right? So what it knows is how to like get trained based on some puzzle to kind of solve the puzzle. That's the pre-training is happening as we're running the stuff. With the Sudoku and Maze stuff that they're doing, they are able to pre-train it before, like they do the validation, and they can have some generalization. But the RKGI thing, no. Like as you run it for the validation, the test, you actually have to train on the data, which is where people were like, "Wait a second, what the heck is happening? Like we're training on the data that we're seeing here right now. How is gonna be like generalizable? It's just data augmentation that we're doing. So we're gonna actually take a look at that. Okay, cool. But that's pretty much that. Okay, cool. So if we take a look at it, and you can check out this video for more information, right? So there's the big RNS at the top, right? I'm gonna go top and then down. Assume the HRM work, right? So what we get for the RKGI is these things, right? So this is the input, this is the output. You get this one pair, you get another pair like this, and the third thing that you get is just like one input. You just get that, right? Then you have to do the output. So what they're doing is they're gonna take all of this, and then they're gonna do a bunch of transformation, a whole bunch of them, right? And then they're gonna take that and then like keep it as some form of information. They do that on like all the example. You only need to do it with 300, but you can do it with more. Also work. And in the HRM, they actually have a specific embedding for it, which is kind of important. It's kind of condensed way of saying like this is how we transform, right? So then it goes into the HRM and it will train with all of these 300,000 example on the same data point, right? And at the end of this is you're gonna like retransform it back. So you're gonna do the reverse kind of transformation that you did at the start. With this, you're able to like get answer for the 1,000 that you have, right? That are reversed now. And you do a majority voting of like which one appeared the most, right? And then you give the two most likely one, and it's a pass at 2 for RKGI, then you're gonna get your answer. So this is the whole idea for this RNS. Inside, what actually is happening is this, right? You have the high level encoder model and then a low level encoder model, and they're like stitched like this. The high level doesn't see the input; it sees its previous state, and it sees the output state of the L encoder, the low level encoder. And there's no difference between the two; it's the same model at the start. It's just that they diverge afterward with what they're learning in their weights. So they have this tick kind of going. This one will recurse with itself multiple times. And after, I don't even remember like how much it is. Like after some time, it will just like output something to this, and then this will output it back, and then keep on going. And then this cycle will continue for like whatever, right? So that's the idea. And then at some point you're done. You're gonna give the H model state to a linear head, which will do the reverse transformation from the like latent space to the actual output. And then this was going to give it to a loss, and then you're going to decide what you're going to do with it, right? They're doing one-step gradient, meaning that like even though like these things are ticking and then running, they're just going to take the last state in order to do the backpropagation. So they're not doing backpropagation through time, which is hell on earth, right? They're doing a fixed like a state backpropagation. There's some criticism about this because like it hasn't converged on any. There's no equilibrium at all, right? So if you're doing one-step gradient on like on non-converged element, it's a bit wonky. So you can sidestep that. Actually, you don't even have to do this the whole thing. Then there's this whole Q head type of thing, right? You don't need it technically, but like if you don't, you're always gonna do 16 of this big iterations, right? And most of the time, yeah, it shows in the paper that like it's not gonna help, right? You're gonna actually overfit on some of data points, so you're not gonna be generalizing that much. The Q head actually is useful to be able to kind of with reinforcement learning decide if you should stop or continue, right? In their case, there's actually two elements that goes into the loss: the halt and the continue, right? So halt is like we're out of this shit. We're just gonna go and do the output. The continue is like, we should continue doing this stuff, and the two kind of laws are like kind of fighting each other, right? Yeah, this is the idea. So this is still in the TRM, but like the continue is gone. We just need the halt, and the halt is good enough for our purposes. And the idea is that like it doesn't show it in the paper, but having the continue and the halt actually create another pass that you need to go through the network, another forward pass, which is like computationally intensive, right? So if you can reduce this computation, you actually can be able to do more useful run. So like the HRM look like this. In anything that they showcase at the end, it's always like 2 low-level step and 1 high-level step done 2 times. It looked not that much, honestly. Like in the paper, they said like they tested 7, whatever. But like it's just this: you do 2 low-level and then 1 big level 2 times this whole thing, and then you output your stuff. I don't know. It feels not that much. And then this you run it like multiple times. You can run it this up to 16 times, right? So there's these 3 levels that are running, and we're gonna see a bit here, like the relation to the mice kind of study, which in my view is weird because in the mice study the frequency is much higher in like both regime, right? So it's not even in the same scale. Anyway, so that's this, and then like the one-step gradient thing. Well, how they do it is that they're gonna like run the stuff and not like accumulate any gradient, and then they're gonna detach, and only at the end they're gonna actually do the gradient stuff, and then have a gradient calculated. So when they're gonna backpropagate over here in this computational graph, they're just gonna backpropagate over there, and then that's done, right? So they save and compute like that. So that's the HRM in absolutely a nutshell. It's in the same family of these type of model, right? So there's also compressed arc that you should take a look at, which is there's no pre-training. And basically you have a model that is kind of doing program synthesis type of stuff. Like they're actually learning the program in order to do the thing. Here it's doing it with compression. So they're going to compress this, and there's going to be a reconstruction loss. They're trying to like recreate it. So if they're able to recreate it, right, like the solution like this, right, through a compression algorithm, it means that like you should technically be able to like predict this one just by compress, decompress, right? Actually, this can get like some pretty good result. You can see here 50 step of learning. This is like the average thing. It's not that great. And then this is like getting better and better. And at some point it learned after 1,500 step what to do, right? It is not overfit technically because of like the reconstruction you're doing, and it needs a lot of data augmentation, which is in the similar vein as that. The issue with this network is that it takes 138 hours, which is absolutely crazy, because you need to train at the same time. So it's in the same regime in terms of like it takes a long time because you need to train, but it fit in the 12 hours cutoff from for arc here. Okay, this is the HRM, and then like in the HRM they show the nice little mice brain here, and then show that like there's different regions that are doing more like strategic stuff with the participation ratio, and then other that are doing like more lower level stuff, and they show that like when their thing is not trained, they have the same kind of participation ratio, and when they're trained, the participation ratio is like at the high level for the high level element, at the low level for the low level element. So there is this hierarchy that is getting created because they actually are. There is a hierarchy. They are working on 2 different things, right? But the thing is, you don't need to have explicit hierarchy like this. You can actually have it in one thing. And the actual study that they based this whole thing on is this one with the mice. It's good. It's there's nothing wrong with this. And then like there's 2 phases. There's this phase with theta, and then there's the low gamma frequency range, and it shows there's a coupling when they're doing this kind of like experiment with mice where they need to figure out with the context of the room which like bucket of food to there is a reward. My issue with this is that there's a whole bunch of other processes. It's not just like this hippocampal region that is like doing everything, right? There's also the connection to the motor cortex and whatever they need to synchronize, whatever. It's much more complicated than that. So like, yes, it's great, but it's so far removed from the actual synthetic stuff you guys are doing that like I don't even see if it's relevant, right? And at first I didn't think it was mice. I thought it was like talking about like the oscillation in the brain, like the alpha and gamma oscillation, or theta and oscillation. But it's not even like human related. It's really like mice related, hippocampal related. Yeah, so that's HRM in a nutshell, right? This is what we have. We have these kind of three elements that are regrouped, and it's kind of difficult to draw. Like that's kind of a litmus test also. Like as soon as you have something difficult to draw in architecture, yeah, it's not usually not the one that stick around the most. So we're gonna review a bit HRM weak points and TRM fixes. Before that, any questions that we have? We have a few here. Is there even a reason for the one-step gradient? Is multi-step too expensive, or is there a non-diffusion step in between? No, yeah, they're doing that one step because they didn't want to go into like backpropagation through time hell, which will have like exploded the compute time. In the TRM, we can do away with this because it's a much smaller network and everything, and it's not going for a long time. But she even says herself that like if we want to go and do more iteration, we're gonna need more memory to do the stuff because we don't do this one-step approximation element. So she can push it like very far. You technically, if you have the compute right now, folks, you can do the same thing TRM but with more steps, and you should get better results. And you can publish that if you want to. So they're applying it to self multiple time and only calculate gradient in final step. Yes, that's kind of what they're doing. So that like you remember, there's just two network, and one network is just like passing through things multiple time. Another one is like also taking the stuff and then passing it through, and like it's iterating like this. And then the last step, the state in the last step is what is used in the back propagation. I actually have like I unroll it literally to show you folks what the heck is. It's not beautiful. I'm telling you, right? So here's how it looked like unrolled, right? It looked like this for the HRM. So this is 2, 2, and then you have the 1 applied twice, right? And this is what you get, right? You get like this, doing this stuff, and then it goes to this same model, same weight, and it goes here, and then go back here, and then this is what they're saying is the equilibrium spot for the one-step gradient. This is related to the deep equilibrium network, right? And then like this is where this state that we're taking. We're not doing like this and there and then there and then whatever. We're just doing that specific state. And when you're doing deep supervision, so doing this multiple times, so this is the big auto loop that you have this thing, which is disgusting, but like this is actually what's happening. You're doing this, right? This is step 1, take the loss, shove it back there. And then you continue, right? You feed the last state to the next thing, and then you do the same thing. You take the loss here, jam it here, and then done. And then you do it again, right? Again and again until like you converge to something, or like you hit the number of iteration. Actually, it's like the thing that will tell you to stop is this Q head over here, right? This will tell you like, okay, now we're good. Let's continue. Yeah, cool. Anything else, folks, before we move on? If you have compute, you can do everything. Yes. You can just do more of it. But also, if you don't have compute, you can do interesting research like she did just right there, right? It's pretty cool. She could have worked with LLMs and just like crank them up. But now she found something that is very interesting. 7 million parameters. She can run by herself and write one other paper that has a significant impact. And like, here am I talking about it, right? Yeah, cool. So any question? Each step it will try to generate a full answer, or steps. It is if it fall very close to different. Yes, each step you have a full answer. You actually have a full latent answer, right? And then this latent answer at some point will be translated to the actual answer in like the real grid space. So that's it. Hey man, what's up, Sharp Eye? We're doing this stuff. Don't hesitate if you have a question. Do you try running this? No, not yet. You can try it. It's all open source. Okay, so let's take a look at a bunch of weak points and let's see how the model is addressing them, right? So one of the weak points that she says is that the deep equilibrium gradient approximation is kind of wonky. That's paraphrasing here, but that's what it is. Wait, web question. Is model very niche to this benchmark? Yes. It's just a puzzle solver here. There's no language whatsoever. We're saying that language is next step. So that's that. So we're all getting very excited for puzzles, guys. Sudoku, maze, we love this shit. So the first issue that we have with this is that with the HRM is that we need an equilibrium point in order to do this one step like approximation, right? This is coming from the DUQ kind of literature. So when you have these models, you can do like fixed point iteration, but like HRM is only doing 4 recursion, right? It's not even like going there. And so even if you assume that the fixed point is reached after X amount of time, I think like they assumed after 7, we're not getting there in the elements. So the 7 n and 7t, we have n equal 2 and t equal 2. So what she's saying is that the residual for ZH in the actual visual in the HRM is above 0. So this is like we're not converged, and the residual for ZL only become closer to 0 after many cycle, but it's still above 0. And ZL is very far from converge after 1 FL evaluation at t cycle. So like this whole thing is not great. So we should do away with it. Like if we can do away with this, theoretically speaking, we should get better performance. We have a comment. You look dehydrated. Thank you. I'm going to drink a bunch of water. I am now a bit more hydrated. We have somebody saying, I'm generally so bad at reading papers, and honestly, it's scary sometimes. It's a scale, man. Like, look at this, right? This is how I end up reading paper, right? It's not linear. There's a whole bunch of information I'm plugging from everywhere. And it takes time, right? Like the TRM, I was looking at it for a full week, like trying to have ideas and stuff and understanding. So just read more. So the TRM kind of fixed this by doing 2 things. First thing, they are literally just unrolling everything. Just what they're doing. They literally said that, like they take these iteration, right, that they're doing, and they just unroll it completely, and they just backpropagate to the full thing like that. It doesn't like we don't have to do it just at the end here, right? Let's actually do it on the full thing. It's not an issue at all, right? And since you have one network, it's a bit easier than you have 2 network and it's all fucked up. It's just one network and you go from top to bottom, and then you make your computational graph and you're done. So that's that. However, right, we're not doing this all the time. We are doing for t-1 recursion, no gradient. So basically what happened is this, like, so you have like this recursion amount that we're doing here, right? Like this. And let's say we're running like, I don't know, like 4 times, right? We're gonna run it once here, we're gonna run it once, run it twice, run it 3 times, right? So this is no gradient, no gradient, and no gradient. And only the last time we're gonna actually have a gradient, right? In here, we're gonna have a gradient. And we're gonna do the gradient stuff on the whole thing. And this is where we're gonna do the backpropagation. So it's kind of the same idea of like 1-step gradient type stuff, but the whole step is the whole sequence of element. Versus the HRM, we were doing like this stuff, but only doing it like with on this element at the end, right? Through whatever iteration that we're doing. So like if you block them together, you don't have to have these weird one fixed like equilibrium element assumption. You can just do it straight on the full element, and you're good to go. Like you will literally backpropagate through all of these elements, and it's gonna be fine. So that's kind of that. For those getting into paper reading, okay, tell people, okay, yeah, cool. So this is the first thing, so you get the benefit of both. You get the benefit of the correct backpropagation update that you're doing, right? But also doing the recursion-free type of thing. Because here they're saying by the design of the deep supervision goal, running a few full recursion process, even with a gradient, is expected to bring us closer to the solution. Because as you run through them, you're updating the solution, right? And it's like, it's useful because you're increasing the effective depth of the network while doing this, right? So you can actually increase it up to 300 like layers, which is very important when you have like these kind of grid where you have to kind of backtrack and test stuff out, right? The other thing that they did was actually try a whole bunch of stuff. So they tried a compromise between HRM one-step gradient, which backpropagates to the last two recursion, and their whole thing, which is like the n+1 propagation. What they see, it didn't help generalization anyway and made the approach much more complicated, right? So it was not helping. So they took the simplest route here. Propagating through the whole n+1 recursion makes the most sense. And they also tried other stuff with the deep equilibrium thing to replace the recursion step by fixed point iteration as done by deep equilibrium model. However, this slow down training due to fixed point iteration and lead to worse generalization. This highlights the fact that the converging to a fixed point is not essential. So the equilibrium idea here is not helping in any shape or form, right? And what I love about this is she actually went and did it. She went to the full extent, and I think had like failed experiment. So like this is good. Like so you can know that like this methodology that she's using is sound because she actually tried the alternative. We have a few questions. So hey, CMN, have a good lunch. But they say that if network size increase, it doesn't generalize also. Yes, because it's overfitting on the task. That's also what she's saying. And then, but she didn't say try it into RKGI. So this is the part because she didn't have enough compute. So this is the part where you can technically increase it a bit. We have a question. What is software used for whiteboarding? It's Still Draw. Right, it's over here. Right, love this stuff, and like this app is great. You can check it out over here. Shout out to Steve. Right. Sometimes they do sponsor my stuff, but I love the app. It's great. Any other question before we move on to the next thing? So one step gradient is cut off completely. We're doing full like sequence backpropagation, but not all the time. Sometimes we're doing nothing, right? But it's good because we don't have to have these equilibrium assumptions. Okay, so weak point number 2 is because of the ACT, right? So the adaptive compute time type of thing. So this thing, right? Remember that over here, this stuff, right? There's some issue because we're doing 2 times the forward pass. So the Q learning objective rely on halting loss and continue loss. And here you have actually had to go and look at the code for that. The continue loss require an extra forward pass through HRM with all 6 function evaluation that we saw previously. So these ones, right? E over here. So these function calls here, which kind of slow down a bit like it's not like that great. It required 2 forward pass per optimization step to be able to know the halt and the continue. So they decide to not do that, right? So they get rid of the continue loss and only learn a halting probability through a binary cross entropy. So in the network, it's actually this. Where is it? Here. The binary cross entropy loss is over there. Jan in here. And that's it. So this is when they know like they reached the correct solution. They don't have to run that. We tried removing ACT with the option of stopping when the solution is reached, but we found that generalization dropped significantly. Stopping and with having like the N16 kind of iteration. And they said it can be attributed to the fact that the model is spending too much time on the same data sample rather than focusing on learning a wide range of data sample. So like this was surprising to me. ACT is helping generalizability in this specific case, right? That's super interesting, right? So that like spending the right amount of time on, let's say, the easy stuff and the hard stuff. Because if you think about it, like ACT help your model spend more time on the hard stuff and less time on the easy stuff as it's learning and it's progressing. So it's changing its parameter on like the harder element. That's actually pretty interesting. It's kind of unrelated, but it's a trend that I've seen also with LLM where like it's no use. It's hurtful to give your model easy stuff. It just creates noise for nothing, right? So actually, it's much better to have a model that is able to kind of know and just like get fed like high quality elements that are kind of hard, especially for reasoning type of thing. So there's maybe something here also. Like there's maybe something about like I had this weird idea of like sorting the element by difficulty, right? And like the chances that like the model will get them or not. And then like feeding them in order type of stuff, right? So at first the easy stuff will be hard because you don't know. But as soon as like it's not spending that much time, cut this thing off and then just go into the medium size, and you will spend a lot of time and then you will reduce. And then as soon as it reduces too much, you cut this thing off. It's kind of similar to actually like the you guys remember the yellow, green, and red methodology for like learning, doing exercise that I showed a while back, like beginning of the year. Same thing as this. If you have green exercise, you don't do them anymore. There's no point. Like if you're doing like math exercise, you got this thing right the first time. Good. Don't ever touch it ever again. Because if you're gonna improve, like it's still gonna be easy. You got it the first time and you know jack shit, right? And then as time go on and you're doing multiple passes on this data set of exercise, you're spending more and more time just on the hard stuff. There's something deeply philosophical here about that. Like I think, yeah, man, I think there's something there. What region is that accent from? Oh, my accent is completely messed up, right? So, like just some background. I'm from Algerian descent, so Algeria Kabyle, right? They speak like Arabic, French over there. I didn't live there that long. I went to Tunisia, Vienna, and all this stuff. I came to Canada, and my accent, the primary thing I'm speaking is French, but not French from France, French from Quebec. So there's an accent over there. I'm taking this accent and this messed up kind of like a background into English. This is what you're hearing. So enjoy. Okay, this is it. So they cut the forward pass like this. Yo, so québécois, hey, comment ça va? Vive le Québec, les, wouh! Ok, on va le faire en français le reste du live, tout le monde. Il n'y a plus d'anglais qui se donne. Joking, we're just going to do it in English. So, the third element is the biological interpretation. She wanted to kill this off because it's true, it kind of doesn't make sense. Like, it was nice to see the brain in the first. I'm from a neuroscience background also. Like, it was nice to see a brain thing in a like an AI thing, but it was pointless. Like they mentioned it at the start, but like it was not helping at all, right? So there's not that much information we can glean from that. They tried a bit, but it's kind of they tried to shoehorn that into the model. But what she's saying is that there's a simple explanation for why this thing is happening. So the first thing she's saying is that like, hey, how about we use like one latent feature or three or more? Like why two, right? Why is two working? And they actually tried it, right? When you use two, you get the best score, all saying the same. When you use 7, you get a worse score. And then when you use 1, right, you get an even worse score. So what's going on, right? And the first thing she did, which is not helpful in the algorithmic sense, is just to like restate what stuff are, right? So in the TRM you have this, right? You have this FH over here, you have this FL, right? And this is what they are used, and then like the Y hat only appear here. But in her case, she says like this is not what's happening. So what she says that ZH is the embedded solution. It is still a solution, right? And then the other thing is the ZL is not an embedded solution. It's something else. It's a scratch pad for the chain of thought. So on the other hand, ZL is a latent feature that does not directly correspond to a solution, but it can be transformed into a solution by applying this transformation, and then you get the ZH, right? So this is what's going on. So like, where is it? I think it's here, right? So you improve the latent here. So you improve your Z, right? So this is the scratch pad, and then this is the ZH, right? So this was the ZL before. This is the ZH, but now it's not called ZH. It's called Y. It's like the latent Y, right? Which makes sense. And like what she did, it's in the appendix, but she showed it with the Sudoku, right? So this is the input. So you have the X, which is something you give all the time to know where you start from, right? And then this is the output Y, right? So this is the output answer. But this is the latent output Y, which is the same thing. This is the answer, right? So before and after, like this is like a represent the actual answer. And this thing, when you try to kind of bring it to like the same space as this, it's nonsensical. Look, there's like 6, 6, 6, 6, 6. It doesn't make sense. Here, it actually does make sense. It tracked to the same solution that you see on top here, because it actually is that, but in latent space. And it makes sense because the only thing that you're doing to do the transformation from this and that is this reverse embedding kind of thing, which is like you take the Z and you have a linear head that is sole job is to give you the Y. So you take like whatever you did here to get the embedding, and you do the reverse at the top. Yeah, so I found that this was very useful because this here is, if you think about it, is a chain of thought that we always see with LLMs, but in a grid space, right? So maybe it's like really trying to figure out where the 6 is going here. I don't know, right? Actually, it's looking at 6 kind of all over the place. So it's maybe like looking this more over here. Yeah, that's kind of like it's hard to understand what exactly this feature is, but like it's what it's using in order to kind of improve and figure out a solution. And then like you have the second step, which is here, right? That second step, which is going to take this kind of fucked up grid, but that actually contain a note, and then look at its actual latent representation of it, and then kind of like take some information to be able to change the Y. If you have only one, so this is getting lost in this. So if you have only one, what happened? If you don't have like the Z and the Y, right? What's going on is that like your Z and the Y is connected together. So most of the time, like you're trying to take notes at the same time as like giving the stuff that you're gonna like give the things to the grader at the end, right? And if you have more than 2, it doesn't help because you're technically breaking this grid into sub compartment technically, right? But all of the feature could be here. It's enough space for it to be there. So that's kind of that. Like this is the whole explanation, is that there is this hierarchy. There's these 2 features because one is the actual answer that you're keeping. Like, yeah, imagine you have 2 sheets of paper. One is the actual answer, right? That you're trying to like fill up from time to time. Another thing is a scratch pad, which is you can mix it up. It doesn't matter, right? If you break the scratch pad into like 7, it just confuses you. It doesn't help that much. Well, that's the idea, right? So this is was super eye-opening and explained a lot, honestly. And then like they also like realize that you don't have to do this with 2 things, right? Like 2 network. The 2 set of weight is not useful here. So here they're saying, while FL iterate on a latent reasoning feature, the goal of FH is to update the solution. But you can have the same network update both because they are separate entities, like it's separate things now, right? So you have the prediction and the latent reasoning, which are 2 things, right? Before, these were kind of stored into the weight of the model, the 2 different model. But now if you store them into like separate grid, you're good to go. And since Z contains X, but Y does not contain X, the task to achieve so is directly specified by the inclusion or lack of X in the input. So this is how it knows what to do, right? So if you have the input X given, you know you're in the regime of like updating the latent thing. But if you have the prediction and the latent only, not the input, you know you're in the regime of like updating the answer. So that's kind of that. So this is the main stuff that this model is fixing up, right? There's other stuff that she's using to tune it up, but that's basically it. So any question before we move on? Love our Quebecois folks, yes. And by the way, Alexa is from Montreal, Quebec once again. It should have like the Quebec flag floating somewhere. Yeah. Do you think different parameter region are used at each recursion, or is it refining at each step? Oh, that's super important. It's super interesting. I don't know. Honestly, I'm not sure. It would be very cool to see, actually. Like, I think that you see, guys, like this is what I'm talking about. Like that stuff, these thought that you guys have while we review this and what she didn't do. This is how you do novel research. So, technically speaking, you can look at the parameter weights, right, and how they change over time, to the progression of the thing, and also which part is changing given which step that you're in. You quantify that, you have yourself a nice paper also, or at least like a portion of a paper, right? So that's a good question. I don't know. They should definitely take a look at it. So this is good. Let's dive into this whole thing. So the code is there. This is a pseudocode, right? So like this is the main kind of loop that we have over there, right? Q at is like decide if we stop or not, right? And Q at, they're not showing it, but there's a Q head that we're using that is getting trained and whatever it is, and then we'll output halt or not. So then you have the steps that we're doing. So the steps are maximum 16. So end supervision is 16, and then we get the input embedded in there, right? So with our X input, actually this should be up. No, because it's, yeah, this, I think this should be up here because we don't need to embed it every time. This doesn't change. So this should be up. And then we do the deep recursion type of stuff, right? We're gonna get our Y, Z, and Y hat, Q hat. And then we calculate our loss with our cross entropy. There's actually two. Earlier I said like this was it. It's like there's actually two loss there. That is not here. There's one here and then there's one over there. And so we have our binary cross entropy and then our softmax loss. We do our backward, we do our optimization step, right? And then we're good to go. If we need to stop, we stop, right? And if we look at deep supervision over here, so sorry, deep recursion. So we do recursion t minus 1 time. So if t is equal to 3, right, we're actually going to do it 2 times without any back propagation, any gradient accumulation, and only 1 time where we're actually going to attach these elements to the computational graph, right? So we do torsional grad and then we do the latent recursion here, and after t minus 1, then we do 1 step with the latent recursion. But remember, the latent recursion is like the whole thing, so it's the whole iteration. So if you look at latent recursion, we're doing this like 6 times, right? So we're doing 6 reasoning step on the Z, and then the last step is to update the Y. So you work with your scratchpad 6 times. So you do once and you look at it like, ah shit, this is garbage. And you look at you see here, you can look at the initial question. So this is your anchor. You can look at the Y. This is where you're at right now with your like crappy solution. And then you have your Z, which is like your current thing, that's your scratchpad, right? So you look at these 3 things and then you do it once and it's garbage, and then do it again and it's garbage, and you do it again, and you do it 6 times like that, right? And you optimize that. Not optimize, you reason through it, right? And at the end you hand your Z to yourself, but now you're only looking at the Z and the Y, right? And then you decide how you're going to update the Y. So you're not touching the Z, update the Y. You return Y and Z, and this is what you're returning here, right? And then what you do, take a quick nap, you come back, and then you do it again, right? And you do this kind of napping thing 2 times, and as soon as you're done with your second nap of the day, right, you're actually gonna do it another time, but then you go to sleep so that you can learn tomorrow, right? This turned into like a nap / sleep, but this is actually good. There's 2 nap you're doing, there's no brain related like learning really that you're gonna be doing a bit, but not too much. And then like you go to sleep to actually do the actual like weight change, right? And that's it. This is the whole thing. There's nothing much, man. It's like it's pretty just that. Yeah. So this is it. This pictogram actually is very useful. So take a look at the blue, red, and purple thing, and then take a look at this. Yeah. So remember, folks, right? Like this is not just this. The data augmentation part, massively important. You like the data augmentation is this stuff that is happening. This harness is still there. This whole thing over here, right, is still the same, roughly speaking, element. And you need that, otherwise you don't have training data for the TRM, right? The hyperparameter, there's nothing like too crazy here. There's like they're using LMW, like most of the stuff are pretty standard, but she showed something very interesting, right? So there's some additional tune-up that she's doing, right? But with a caveat. So do read that, right? So this part, while our approach lead to better generalization of 4 benchmark, every choice made is not guaranteed to be optimal in every data set. And they show that because some of the configuration are good on Sudoku Extreme, but not on the other stuff, right? So for example, the attention we're gonna see can be switched up to MLP and should be good to go. And then you don't have to do 4, you can only do 2 on the Sudoku and it's good. But if you do 4, it's better, I think, on the RKGI, right? So there's all of this, which tells me that like, it's not about the 7 million parameters, right? If we actually do a good latent reasoning model that understand language and whatever the heck it is, right? I think you will have more parameters to be able to know a lot of stuff. But like the architecture will not just be like MLPs and what, like attention is actually super important. But it depends on how much it's trained and how generalizable it is. So the final version of this stuff will not be just like a very tiny model. It will be, I think it will be smaller than the bigger one, right? That we have, the gigantic stuff, but it will be just a bit different, right? And I think we're starting to see all of the elements coming together. So like the halting procedure being important, being able to weight which elements are difficult or not. I think this is inherently something that makes a lot of sense from like just human experience. Like if you spend a year doing easy problems and I give you a hard one, you're gonna fail for sure. Like you don't know these art stuff, right? If you spend the whole year just doing hard one, like it can still work. It's gonna be hard for you to like learn at the start. But if I give you a mix so that like the difficulty is increasing and whatever, and at the end you're just doing the hard stuff, the chance that you're gonna do good are very high. And this is like human like approved, right? In our brain, it's like kind of how like learning is best applied. So I think like these elements will be important. Okay, so enough of tangent. Here what they're saying is there's like 5 things. Here, first, less is more. You don't need to have like a lot of layers, right? They're saying surprisingly we found that adding layer decrease generalization due to overfitting. Does it mean that for other things we'll have very small amount of layer? No, right? It will most likely be more layers because we need more layer for RKGI than the other stuff. It just means that like, look at what we're doing, guys. It's puzzles, right? You don't need to have crazy amount of layers. And remember what's happening is that you're actually having high effective depth because you need that to do the hops, right? It's kind of what we're doing here, right? And it's important because the transformer can't do that because they have a fixed depth and it's not enough in most cases in order to do the hops because it's a puzzle, right? And puzzles, sometimes you have to change stuff and then try things and then go back and do this thing. And we know you don't need to have massive amount of layers because we can deterministically create this program, which isn't a million lines of code. It's a few lines, right? But you can create a program that will do the backpropagation, the backtracking type of thing. But here what we're trying to do is trying to have the backtracking and whatever happening inside of the weights of the network. We have a question. Do you think would directly be trained on language? It would be hard. Like training this in language, it would be a bit difficult, but I think it's possible. I think like, because if you think about it, like look at what you have, right? We have this, right? You have these 2 elements. You have the prediction and then you have latent reasoning, right? Which is a scratch pad, technically speaking. And you have the input that tell you like where you're at. So it's totally possible, right? So right now the chain of thought type of thing are happening with the reasoning being happening outside. Very wasteful. It's like kind of garbage, right? But there exists other architecture. Like let me show you this one. Yeah, this one. This paper over here. This one, right? Like in this paper, see here, there is this idea of like, how was okay guys, Senti is back. Hi Senti, how was the food? So in this paper, it's a 2019 paper, right? They show that like you can increase the effective depth of the network by having this kind of like a recursing line, like a link in the model. So the model will not just like go through all of this and then go there and then go through all of this, right? Like a normal transformer, right? It will go through this and then it will iterate again and then refine his stuff within the same amount of weight. So what you created is like effectively you can have more layers, right? Theoretically speaking, it's the same weight. They're the weight are shared through like these iteration that you're doing, but that's it. So like if we were to make like a LLM as they're constructed today, you could take this part, just this part over here, and that's that, right? You just take that. So you get this, and then like you can do the latent reasoning not in the chain of thought, right? So it's inside the model own space that you're doing that stuff. There's change to this to make it like more performant, whatever, and the TRM is like kind of showing us what change matters and what not. But this is still puzzle. So language will be the next frontier to make them useful. You should also check out the CTM. They are doing other update on it, but we already see kind of this kind of reasoning in latent space being very, very powerful with like a small model weights. It's different. It's like neural oscillation in their case, but it's the same idea of like the latent scratch pad is inside the model, and it's using that, but it also having an output that is like updating. This motion, absolutely important, right? And the CTM also, what's cool with it is that it has the same kind of property over here where it can know which element is hard or not. So you like, yes, it will take more time because you need to do these ticks motion inside, but at some point you will know if you're done with the data point, like, hey, my confidence, right, entropy, whatever it is low here. I'm good enough. Like a check mark. I'm gonna move to another element, and then you can iterate like this and kind of know what to do. Yeah. Also, they're saying like it doesn't matter to have more layer because the data. If you have more, if the data is scarce and then you have a lot of like parameter, you lead to overfitting, right? If you have plenty of parameters, you can have more layers, and like you can even overfit and then go into the grokking mode, which is like past overfitting, which then the performance gonna improve, right? So this is good, it's fine, but you need to have like enough data to go through this cycle. Puzzle, you don't really need that, right? Like it's not useful. So this is likely an indication that there is still too little data. Thus, using Montani network with deep recursion, deep supervision appear to only allow us to bypass a lot of the overfitting. That's a very interesting element here. Also, attention tree architecture, you can replace for which one? The multi-layer perceptron. You can replace the self-attention for the Sudoku extreme, right? So like the Sudoku thing that they're doing, it's a hard Sudoku. However, we found this architecture to be suboptimal for tasks with large context lengths, such as the maze stuff and the ArcGI. Maze and Arc, they need self-attention. In this case, they could change the self-attention for MLP. So here, instead of having self-attention, you could actually have an MLP and be good enough only on Sudoku. So like what this shows you, Sudoku doesn't matter, folks. It absolutely doesn't matter. It just shows you that there's like some tasks that require a different architecture, but that self-attention in general, when the context is increasing, right, is useful because then you can like know which part is important on which. CTM also use an attention mechanism inside of the model. That's good. This architecture will apply for specific task training, right? For example, only for Sudoku solving. You can generalize, I think. Like you. No, it'll be fucking a mess if you do that. No, it's like it's trained and tested on one thing at a time. So like you're training like purpose-built TRM for Sudoku, purpose-built TRM for the maze. I'm pretty sure. I think like this one I have to double check, but I'm pretty sure this is what's going on. I think in the result we see that. I don't know if it's the same model for both. I have to double check. I'm not sure. Yeah. But I know the RKGI one is only trained on RKGI, and they run it like that. Exponential moving average, they're using like the EMA, it's a technique from the GAN and diffusion model. So you see there's a connection, you're right, like I don't know who said that, but there's a direct connection to diffusion modeling, right? I don't know folks, like it seems like it seems there's like some elements of latent reasoning or like working on the thing multiple times as a scratchpad being super important. Like for me, that's what I'm getting out of this. Like test time scaling, absolutely fucking useful. And I've seen that also at the conference, like the language modeling that I went to. Even at big LLMs, like test time scaling is super, super duper good, right? You're not changing the weight, but like you're doing more compute to do that stuff. But you're doing it like also in token space, right? So if you're doing it in latent space, it seems to have a big gain. We have a few questions. What is the intuition that billion parameters cannot learn this and this paradigm does better? This is just because of their fixed network depth. That's all there is. And subsequently, can we embed this type of network in billion parameter for future improvement on ARC? It's already happening, right? So this is actually a super duper good question. Thank you, Akash, for that. We're gonna take a look at it here. So now you are inside the board. Over here, right? This is the question, right? So what is the intuition that billion parameter cannot learn this and this paradigm does better with such less parameter? Check out the video from Julia Turk, because she showed it really well in the first few minutes. The LLMs are fixed depth. So like if you go through it, the model, this is the depth you have. The chain of thought help you kind of get more depth, but it's still like a kind of a very artificial way of doing it, right? And why do we need more depth is in this particular puzzle, you're gonna write something and it's gonna be wrong and you have to test different direction until you find the right path. It's kind of like a tree search that is ongoing, right? And like subsequently, can we embed this type of network in billion parameter to further improve our ARC benchmark? You don't have to. What you can do instead is use like Berman over here, the LLMs in a kind of hierarchy, right? And like kind of make them evolve their kind of program that they're synthesizing in order to find a solution. So this is what this guy is doing, right? Which is kind of helping the model with this depth problem, right? That's roughly speaking. And like he's getting like some super good results with Grok, I believe, because he's what did he do? Like he was using them to with the evolutionary algorithm to figure out like what instruction it should give. So it's kind of evolving the scratchpad, right? But like helping them out with the harness, kind of the same thing that we're doing here. So this idea of kind of breaking the barrier of the model like fixed depth is important. And we're seeing it just with the reasoning, we see it already, right? We see it because if you do chain of thought, you give more space to the model. So you have a scratchpad. If you take the scratchpad and jam it inside, right? It's the most efficient you can get, but you don't have to do that. You can actually like just go ahead, but look at the cost. The cost is a bit higher than that. And it's always going to be higher than just like the Grok or these model, right? But the performance is there. So like having a good scratchpad inside the model with as little like a modification between when you're going to do applying the back propagation and like the actual weights of like the scratchpad seems to be something that is kind of fundamental here. We have another question. HRM-based models seem to work good with less step, but over a very long check reasoning, do they suffer? This is just puzzle stuff, so we have to double check that. Like, but if you think about it, RKGI 2, like, it's still not crazy good, right? It's better than like most model, but it's still not like insanely good. It's just 6%. There's still stuff missing in this thing, right? What do the color coding for your highlight correspond to when you? Yeah, you saw that, right? Like, it's more vibe, to be honest, right? Than editing. So like my rough, I don't know, like my rough. This is a good question. Okay, we'll see it. We see it here in full display, right? With it. So green for me is like, oh wow, well this is like some very positive element to it. Yellow is that this is an interesting thing. It's an interesting element to that I should maybe remember. Blue is like, it's like the green, but it's different. It's like, huh, right? More this. And then the purple is a surprising element for me. Like when it's surprising, I'm gonna highlight it in purple. Red is something bad happening, right? Either on the narrative of another architecture or the narrative of this structure. Sometimes I highlight in red because like, what the fuck are they saying? Maybe this is wrong. And sometimes I highlight in red because somebody else was wrong. And I was like, this is wrong. Are they sure this is wrong? And then I highlight it in red. There's no clear basis for this, but this is how I feel. I feel better with that. So then when I read it, I know like roughly, it's kind of embedding space of like how I feel about the paper. Okay, we have another question. How do we know this new model are good if they are training in their puzzle data set very close to ARC puzzle? They're not only doing this, they're literally training on ARC puzzle. Literally, right? So if you're not caught up with this, because this is, me too, when I learned that, I was like, what the heck? Are we even like, is this overfitting? François Chollet also thought it was overfitting at first, but this is good. Like it's legit because you're not training on their answer. You're training, well, actually, yes, you're training on the answer here, but for what is already given to you, right? So I give you 2 exemplar, and then you're going to augment them, right? And then I give you 1 exemplar, which is just the input, and I tell you what is the output. You don't have the output. You can't just like spit it out. So with the data augmentation, what's happening is that you're saying to the model what is important and what is not, right? And so far, you need that. Otherwise, there's no way you're going to train anything whatsoever, right? So that's the setup. This, if you're very interested about that, check out the compress arc element, right? It is legit, right? It's a bit weird, but it is legit. But if you think about it, you're actually saying to the model what is not important. You're saying to the model, translation is not important. Rotation is not important. Flipping the board is not important. And color permutation is not important, right? That's literally what you're saying. So, I don't know, maybe also this is why they suck at the... Maybe this is why they suck at the RKGI 2. Maybe like these permutations are important there. I have no clue. Okay, so almost done, folks. We're almost ready to roll. The last thing is the optimal number of recursion here. They tested a bunch. More recursion could be helpful for other problem, but we have not tested or given our limited resource. Wink, wink. Right? If you have spare compute, take our code. Try this shit out. You can get better performance. And then tweet about it on Twitter. You can even make a paper out of it if you want to. If you like add the rest of the stuff that we discussed. That's it. And like you see here, they like worse than this. They got out of memory error, right? So if you have more memory in your like system, you can try these things and like you can just get better performance. I love this. Like she's like running this whole operation on like limited resources and it just fucking work. Oh man, this is good. Wait, we have a few questions. I guess a commonality with things like CTM, TRM diffusion is that every problem is transformed into an optimization problem rather than given a single output, the output is refined. Yes, right? But then this is bounded. You know the realm of the output you're gonna get out here, and then you're like clearing this up. Yep. Do you know how they augment for RKGI? It seems that each puzzle will need different augment function. No, actually, it doesn't matter if they make a mistake. This is it. Like, even it, like theoretically speaking, even if they fuck it up here, right? They'll be able to know if like the transformation recipe is kind of garbage, and like they're using this puzzle embedding to like condense this information about like how it was changed, and then they're using this. They're literally giving the model that information, right? So then once it's out, it's transformed back, and then you have 1,000 of them or 200, right? Somewhere in between, and then you take the two that are happening the most. They should be good. So if there was some that like where the flipping was important and it all fucked up, all of them will be like wrong, right? So technically you should not see them that often because of the optimization that you're doing here. Yeah. So, but this part is really weird. You should like there's a guy from NDEA that has a whole deck on it. I can try to find it back. Well, what is it? The NDEA HRM Asser Brighton graph. Yeah, this is it. Okay, check this out. Check this one out, right? This is my man, and they have a slide here. Right, check that. It goes into a lot of depth about like how they did that over here. And here's the video. There you go. Okay, wait. We have another question. How can I know about your next video streaming like this? Do you have like a website? Like I used to have like on YouTube, like the prepare the stream in advance, but it was a bit chaotic for a while. I'll mention them before. On YouTube, you'll be able to see like and get reminder. Okay, so let's take a look at the result, folks. This is what we're all waiting for. It's doing good. it's actually good. So you have the what I like is that she did a whole bunch of ablation. So she did a TRM, which is like the perfect setup, and she did it like without ACT, and you get like a 1% drop here, right? So you get a 1% drop, and also it's fucking longer to run. So why should you even do that, right? So ACT is good, and then like you do HRM technically with the separate like FH and FL, and you get like lower performance again, right? And then you double your number of parameters. This was 5, then now it's 10. Then you have a whole bunch of stuff. So no EMEA, so exponential moving average for like the diffusion GAN stuff. You get less performance here. If you use 4 layers instead of like what it was 2 here, lower performance again. Without self-attention, you get lower performance on the Sudoku. Sorry, no, this is with or without. No, this is without self-attention. So this is worse. How is it worse? What did she say here? Yeah, here. Better generalization on Sudoku Extreme. Wow, this is weird. Does she mean like width? Okay, no, yeah, sorry. This is with ACT, so like a lower performance. So actually, no, ACT is lowering the performance over here. Makes sense. With separate FH, FL, we get lower. No MEA, we get lower. With 4 layers, so instead of 2, we get lower performance. With self-attention, it makes no fucking sense. Is this with or without? That doesn't make sense. Oh, no. Yeah, it does make sense. So this one is purely MLP. Sorry, I had a brain fart here. This is purely MLP. So if you add self-attention, you get like a big drop. And then like T equal 2, N equal 2, you get that. Not that great. So T equal 3, N equal 6 is better. And if you have one-step gradient, look at this, 56%. Not that great. So this is the whole thing. So a whole bunch of ablation, fantastic work here. And then she tests the accuracy with like TRM versus HRM in various effective depth, right? And like she can't go that far. You see here 156 effective depth. It just sucks, right? Like it literally doesn't work here and here. But at 84, for some reason it worked in terms of memory, and she got like an awesome performance here, 85% versus 58. Good. And throughout, a TRM is just like clearly better. So the structure of it is much better than like the HRM. If you see here the Sudoku versus Maze compared to DeepSeek, Claude, and O3 Mini High, like they can't do this stuff. Like it's too much backtracking that you need to do in order to get that. So like they are not able to do this. Yes, Nicholas, this is live. We're doing this live. Yeah. And you see here, if you do direct prediction or HRM, you get like 55% here, 75%. So I don't know what direct prediction means here, so I'm not sure. But like you get 55% on Sudoku, 74% on Maze. But if you do TRM with attention, so you get 74% on Sudoku and 85% on Maze. And like the TRM, just the LMLP, Sudoku is good, Maze is garbage. So it's like a mix of the two. So best one for Sudoku is MLP based, and best one for Maze is like attention based. And RKGI is purely attention. So if you look at RKGI, we get Grok is actually pretty great. Like it's not it's 1.7 trillion parameters, so you get 79% over there, 29% on RKGI2. So this is the best model you can have right now for ARC. But TRM at 7 million parameter get to 44%, and ARC2 gets 78. That's like even better than, let's say, Gemini 2.5 Pro, right? Past this cutoff, right? Over here, like this one is much better than all of them, right? Grok is surprisingly really good, and if you look at this element here, right? These two guys, which are literal people that like use the LLMs in specific ways, they can get better because they're creating like a harness around Grok. Grok 4 is the one that is being used over here. I don't know why Grok 4 is so good. I honestly don't know what is good at RKGI. If we knew and this was open, we could actually like understand this better. Maybe it has to do with chain of thought. I don't know. Maybe they're doing some sort of latent type of thing inside. I don't know. And that's it. I don't have the brain cell to comprehend anything right now. We'll probably watch the rec in the morning. Good idea, Andy. Good idea. Yeah, that's it. Like in conclusion, like I don't know, man. I think this is super cool, right? Super good research. Should read the paper, guys. Honestly, like you could read it in less time than like the stream is running, right? That's one thing. And the ideas in it are super interesting. And I see like kind of this trend of like latent reasoning. There's this other paper from a lab that like is closely related to her in Montreal also, that I might like cover in another setup. But it's a mixture of recursion, learning dynamic recursive depth for additive token level computation. This idea of recursing inside and having like this element iterating is not new, but it seems to be a missing piece that we have in LLMs in order to get like better intelligence in general. And it seems to be not something related to scale that much, right? It seems to be a fundamental block, a bit like the residual stream was an important element, right? So for the learning in general, this seems to be another block like this, and like there's all sorts of things that we need to take into consideration. Adaptive compute is one, like all of this, but I think we're getting there. So that's that. How much you would say this differ from HRM? We did the whole thing, dude. Check out the recording. Like we did the whole difference between the weak points and the fixes over here. So you'll be able to check it out. Actually, I think I can share this directly. Can I publish that? Yes. Copy link. You can check it out. Right, sorry. I should have sent this out earlier. So you can check it out. The link is there. You can go into the board directly. It's a new paradigm. Yeah, it's an old paradigm that has been tuned up for like now. But it's honestly something super interesting. That's it, folks. I hope this was useful. I wish you all a great weekend, right? If you have some time this weekend to check some research out, check this one. Like honestly, it's like 9 pages and it's well written, super crisp. Good job, Alexia. Keep it up. Do what you do. Like continue pushing the boundary here. Get some compute. Give some compute to this woman. That's all I have to say. All right. See you, folks.